Question 6. Two identical metal spheres are placed on insulated stands. Sphere A carries a charge of -3 nanocoulombs and sphere B is uncharged. Uncharged is written in capital letters, showing us that it is very important for you to note that sphere B is uncharged. We have two metal spheres, A and B. Metals are conductors, meaning they allow free electron flow or free negative charge flow. These metal spheres are conductors placed on insulated stands. Insulators do not allow the flow of negative charge or electrons. The charge on sphere A is -3 nanocoulombs, which is equals to -3 multiplied by 10 raised to the power of -19 coulomb. Remember, nano means 10 raised to the power of -9. This means there is an excess of electrons on sphere A. That is, the number of electrons on sphere A is greater than the number of protons. Hence, it has this negative charge. The charge on sphere B is 0 coulombs. Because sphere B, it is mentioned that it is uncharged, so there is no charge on it. So it has a charge of 0 coulombs. This means that the number of electrons on sphere B is equal to the number of protons. Hence, it has no charge. It is uncharged, or somebody else might say it is neutral. Let us look at question 6.1. Question 6.1. What is meant by sphere B is uncharged? This is a 1-mark question. I have just alluded to what it means that sphere B is uncharged just now. Sphere B is uncharged because the number of electrons in sphere B is equal to the number of protons, meaning that it is electrically neutral. There is no excess charge. I hope that is clear. Question 6.2. Calculate the number of excess electrons on sphere A. Let's first try to determine what is given to us about sphere A. What is it that we know? We are given that sphere A has a negative charge of 3 nanocoulombs, or -3 multiplied by 10 raised to the power of -9 coulombs. This means that it has an excess of electrons, meaning that the number of electrons in sphere A is greater than the number of protons in sphere A, right? Now, we also know that the charge on a single electron is given by that small letter QE, which is equals to -1.6 multiplied by 10 raised to the power of -9 coulomb. Now we have to find the number of excess electrons, and that is given by the small letter n. We will do this by using the expression that describes the quantization of charge, which is that big letter Q for charge equals to NQE. This means that every other charge in the universe is an integer multiple of the QE value. Every other charge is an integer multiple of that QE value. But we need to rearrange the terms so that we can make n to be the subject of the formula. We can use this triangle over here, where it becomes clear that n equals to Q divided by QE. N equals to capital letter Q divided by small letter QE. Therefore, n, or the number of excess electrons on sphere A, is equals to the charge on sphere AQ divided by the charge on a single electron QE. This will give us that n is equals to open brackets. So it is important when you are working with very small numbers or very large numbers to always open brackets. So you see open brackets, n equals to negative 3 multiplied by 10 raised to the power of minus 9 divided by, open another bracket on your calculator, the negative 1.6 multiplied by 10 raised to the power of minus 19. And this, if you put it in your calculator, it will give you a value of about 1.875 multiplied by 10 raised to the power of 10, meaning the excess electrons on sphere A, they are that many. It's a lot of excess charge. I'm not sure why this is a 2-mark question. I believe it should have been a 3-mark question. But anyway, you will receive a mark for the correct substitution and another mark for the final answer. Sphere A is brought close to sphere B without allowing them to touch. That is an important thing. They are just brought close, but they do not touch. Question 6.3. Describe the changes that take place on sphere B. So if we allow these two spheres to come close, to come near each other, but we do not actually allow them to touch, we now need to explain what changes will take place on sphere B. And the changes that will take place on sphere B is that, remember, the excess charges which are electrons on sphere A will repel the electrons in sphere B. And this will result in a separation of charge in sphere B. So we will have a situation where the side of sphere B closer to the negatively charged sphere A will be more positive because all of the electrons would have been repelled towards the other side of sphere B. Therefore, the electrostatic force, that force of repulsion, will cause the electrons in sphere B to be repelled by the excess electrons in sphere A. So to answer question 6.3, we write that the electrons in sphere B will be repelled by the excess electrons in sphere A, resulting in a separation of charge in sphere B. To get the 2 marks, you must understand that like charges repel and that since the spheres are not touching, we will have a charge separation, not a charge transfer. We only have charge transfer when the two spheres actually touch, and we will see what happens when these two spheres touch in later questions. The two spheres are now made to touch each other and are then separated. Question 6.4. Will electrons be transferred from A to B or from B to A? And this is a 1-mark question. So electrons always move from the more negative sphere to the more positive sphere. It's almost like thinking that the electrons are always attracted to the more positive sphere, right? And we can agree that sphere A is more negative than sphere B. Sphere A, remember, has an excess, has more number of electrons than it does protons. So those electrons will be attracted to the more positive sphere B. So it means that the electrons will be transferred from A to B. So you see that we have the electrons or the negative charge being transferred from sphere A to sphere B. And to answer this question, you can just simply write A to B. Question 6.5. Calculate the final charge on each sphere after separation. To solve this problem, we first need to determine what is given to us. We are given that the initial charge on sphere A which we can call Q1, capital letter Q1, is equals to minus 3 multiplied by 10 raised to the power of minus 9 coulombs. This is the charge before the two spheres touch and then get separated. The initial charge on sphere B, which we can call Q2, capital letter Q2, is equals to 0 coulombs, because they said that initially the sphere B is uncharged, meaning it is neutral. So we need to actually determine Q. We need to find the final charge on each sphere after touching, and that will be given by Q in coulombs. After charging, the spheres will have the same amount of charge. After touching, the spheres will have the same amount of charge. This means that after touching, sphere A will have the same amount of charge that sphere B has. And this is because of the principle of conservation of charge, which states that the net charge of an isolated system remains constant during any physical process. This simply means that we cannot create nor destroy charge. It can only be transferred from one conductor to another, or from one material to another. So sphere A will transfer part of its charge to sphere B until the two spheres have the same charge. To solve this, we will use the expression that the final charge Q on both the spheres is equals to the sum of the two charges on each sphere before they touch divided by 2. This means that the spheres will split the total charge in this system in half. Now, it is just a matter of substituting the known values of Q1, capital letter Q1, and capital letter Q2, that the final charge is equals to brackets negative 3 multiplied by 10 raised to the power of minus 9 plus 0 all divided by 2. And this gives us a value of negative 1.5 multiplied by 10 raised to the power of minus 9 coulombs. What does this mean? This means that after touching, when we separate these two spheres, they now carry the same charge, which is negative 1.5 multiplied by 10 raised to the power of minus 9. So this is another 2-mark question. You will get a mark for the correct substitution and another mark for the final answer. Question 6.6. State the law of conservation of charge. This is a 2-mark question. It is a recall question, meaning it just requires you to remember the definition of something that you have studied. The principle of conservation of charge, or the principle of charge conservation, states that the net charge of an isolated system remains constant during any physical process. So a physical process, as we saw previously in question 6.6, can involve two spheres just touching. That is a physical process. So they are telling you that the charge there remains constant. The net charge, that is the total charge, remains constant. Or somebody else may say that this simply means that charge cannot be created or destroyed. But what happens, as we saw with the previous examples, is that charge can just be transferred from one object to another. Question 6.7. Calculate the amount of charge transferred when sphere A and sphere B were in touch, or when they were in contact. So before touching, sphere A had an initial charge, let's call it QAI, of about minus 3 multiplied by 10 raised to the power of minus 9 coulombs. And sphere B had a charge, let's call it QBI. So the I is for initial, which is equals to 0 coulombs. Remember that sphere was uncharged. Now, after touching, and when these two spheres have touched and are being separated, sphere A now has a final charge of QAF, which had a value of minus 1.5 multiplied by 10 raised to the power of minus 9 coulombs. And sphere B has the same charge as well, which we can call QBF, and that charge is also a negative 1.5 multiplied by 10 raised to the power of minus 9 coulombs. So that is the information that we know. Some of this information for the before it was provided, but after touching it is, we calculated this in the last question. We are given, so let me just list the values, the quantities that we are given. The initial charge on sphere A, I said that charge is negative 3 multiplied by 10 raised to the power of minus 9 coulombs. We also have the initial charge on sphere B, which is 0 coulombs. We also know the final charge on sphere A, which is negative 1.5 multiplied by 10 raised to the power of minus 9 coulombs. And finally, the final charge on sphere B, which is negative 1.5 multiplied by 10 raised to the power of minus 9 coulombs. So we will determine the charge transferred using this expression. So this is the expression. So we will have that the charge transferred is delta Q. That triangle thing there is called delta, and it means a change, and you will work a lot with that triangle in your physical sciences career. So it's important to know what it means. It means a change in. So for example, in this instance, it means a change in Q, a change in charge. Hence, it will help, this expression will help us determine the charge that is transferred. And the one, how we can do that is that the change in Q is going to be the final charge on a sphere, QF, minus the initial charge on a sphere, QI. So we need to find what is the charge. We need to take the difference between the charge, the final charge after touching, minus the initial charge before charging. I hope that makes sense. So we can do this process for either of those two spheres, sphere A or sphere B, and we will get the same answer, right? So if for sphere A, we can say that delta Q, or the change in charge, equals to QAF, which is the final charge on sphere A, minus QAI, which is the initial charge on sphere A, that is before touching. We know that the final charge on QA was negative, so open brackets again. Brackets are your best friend. They make sure that you don't get the incorrect value on your calculators, especially when, like I mentioned, when you're working with very small numbers or very large numbers, it's easy to lose track. But if you open those brackets, you will keep track, right? So we have that delta Q, or the change in Q, equals to brackets minus 1.5 multiplied by 10 raised to the power of minus 9. That was the final charge on sphere A after touching, minus, and then remember the initial charge was also negative on sphere A. So you have minus, open brackets, minus 3 multiplied by 10 raised to the power of minus 9. Put this on your calculator, you'll find that the charge that was transferred, the charge transfer was 1.5 multiplied by 10 raised to the power of minus 9. That is the amount of charge that was actually transferred from sphere A to sphere B. But you can also do a similar process for sphere B. Let's see if we will get the same value. So we'll say that the change in Q for sphere B is that the final charge on equals to the final charge on sphere B, QBF, minus the initial charge on sphere B, QBI. And if you substitute the known values, their final charge on sphere B, we know it was minus 1.5 multiplied by 10 raised to the power of minus 9. The initial charge was that sphere B was uncharged in the beginning. It had 0 coulombs, so we have minus 0. And if you put that in a calculator, voila, you get the same value, the same magnitude. Let me say that. The answer that you get is minus 1.5 multiplied by 10 raised to the power of minus 9 coulombs. Now, I'm sure you have picked up something. What is the sign? The other value when we did for sphere A, we determined the charge. We found it to be a positive 1.5. We do the same process for sphere B. We find that it gives us a negative value. It's the same value, but the other one is positive and the other one is negative. My reason for the difference in the sign is that one sphere, remember the one sphere transfers the charge to the other sphere, while the other sphere receives the charge from the other sphere. So the one sphere gains 1.5 multiplied by 10 raised to the power of minus 9 coulombs of charge, and the other sphere loses 1.5 multiplied by 10 raised to the power of minus 9 coulombs. And I think this is the reason for the difference in the signs that we get there. This is a 2-mark question. You'll get a mark for substitution and a mark for writing the final answer. Question 6.8. Will the spheres exert forces of attraction or repulsion on each other? And you must give a reason for your answer. Don't you hate those types of questions where you have to reason? So after touching, the spheres have equal amounts of negative charge. They have a charge of about minus 1.5 multiplied by 10 raised to the power of minus 9 coulombs. The charge on both spheres is negative. And what do we know is that like charges repel. So the two spheres will exert a force of repulsion on each other because like charges repel. This is a 2-mark question. You'll get a mark for mentioning the force involved, which is repulsion, and another mark for your reasoning. And we are done. Thank you very much for watching. But before we finish, tell me your ideas about question 6.7, especially with respect to the different signs that we obtained for the charge that was transferred. I would actually really like some feedback on that because I'm not completely sold about my reasoning behind it. But tell me what you think. Thank you so much for watching.